This was a walkthrough of section 5.6, bending strength of non-compact shapes. Just a little new formula, but a little bit of conceptual discussion that might be a little challenging, but will hopefully make sense by the time we're finished. But the formula for non-compact shapes that we're going to use mainly for non-compact flanges is really is very familiar format, okay, similar to something we've done for compact shapes, okay. So what I'd like to have you be able to do by the end of this module is to be able to calculate certainly the nominal moment strength or capacity of a section with a non-compact compression flange. That's all we're going to deal with. Then adjust the nominal moment versus unbraced length plot to show that, and then also realize that there's only one change to what you've been doing before when you're calculating nominal moment capacity. Okay. All right, so we just have a few non-compact flanges within the typical hot rolled shapes. Again, this all applies to hot rolled shapes. If you start getting into plate girders, then you have to check everything specifically for non-compactness and slenderness. Often you will get into slender elements, certainly slender webs for built up plate girders. But as far as hot rolled shape, everything that we use is going to have compact webs, okay? No sections have slender elements, okay? And you can see this if you look at section F2, the part that we've looked at already, right? For doubly symmetric compact eye shapes and channels bent about their major axis, that's what we've been dealing with. There's only 11 shapes that have non-compact flanges, and all shapes, right? All shapes have compact webs, okay? So again, it's just really the flanges that we're going to deal with. And the main thing to remember is non-compact sections cannot reach our plastic moment capacity. So we cannot reach M sub P equal to ZX times Fy, because what will happen is the web will buckle, or the flange will have that buckle before it reaches that, right? So the one video I showed this buckled flange, right? So you have a local buckling of the flange, okay, prior to reaching the plastic moment capacity. So that's what flange local buckling is. Again, web local buckling, WLB, we don't have to worry about. We still have to check lateral torsional buckling, right? As LB increases, this becomes more of a problem. And eventually this will produce a weaker moment strength than the flange local buckling equation, okay? So again, flange local buckling only really is a concern when you have short unbraced lengths, okay? After you get to a certain length, your lateral torsional buckling formulas that we've already done will kick in, okay? So you always have to determine the smallest value. The smallest value, right? M sub n is based on the smallest value, be it flange local buckling or be it lateral torsional buckling. Of those conditions, you have to use the smallest value, okay? Remember, there is two possibilities here, inelastic and elastic, okay? All right, so when lambda, okay, and lambda again is a general term for a width to thickness ratio, and in our case it's going to be lambda is B sub F, the flange width divided by 2, divided by the thickness of the flange. When that condition exceeds lambda sub P, and if we're talking about a flange, you'll see in the formulas they're going to do a subscript F, okay, when we get into that equation for non-compact flanges, okay? So we could put a subscript F after all these because we're only dealing with a flange, okay? So we could put subscript F there, all right? So when we have that, okay, we have that lambda value, generic B over T, in our case, B sub F over 2 is half the flange width divided by thickness of the flange is our lambda value. If we have lambda sub F less than lambda sub P F, we're back to section F2. So you have a compact shape, everything is as it was before we got to section 5.6. If we end up with lambda sub F between these two limits, right, we get lambda sub F between these two limits, then we do have a non-compact flange and we use equation F3-1. If we end up with a lambda sub F flange greater than lambda sub R F for the flange, then we end up with equation 3-2, okay? And if we're in this region, right, the flange is said to be slender, and we're not going to really deal with those, okay? We don't have any really in standardized rolled shapes. So if I look at the steel manual, section F3, okay, doubly symmetric die-shaped members with webs and non-compact or slender flanges is what this says in the background, okay? We have to, look at number one, lateral torsional buckling, okay, just like we did before, F2-2, right? So again, that's a function of L sub B. The longer the L sub B, the lower the moment strength. But if we have a compact, non-compact flange, we use this formula. And notice the subscripts P sub F, okay? So for non-compact flanges, right, we have to use this equation. And that equation should look familiar to you, okay? It's a similar format as an equation we used from provision F2.2. And again, if you have a slender flange, you'd have to use this equation, but we're not going to get into that. But notice both equations have S sub X in there, so that makes you think about elastic moment, okay? So those are the equations we're going to understand. And again, if I look at that one equation I just highlighted with the subscript F, it looks very similar to this equation F2-2, okay? And table 3.2 is helpful in understanding this. Remember, that's the table that has L sub P, L sub R, our plastic moment capacity, our residual moment capacity, right? This is M sub R. It's accounting for 30% residual stress, okay? So we can, see a similarity there, right? Instead of using unbraced lengths, L sub B and L sub P, we're now just substituting in our lambda values, our B over T ratios, if you will, okay? So we want to discuss how that affects our nominal moment versus unbraced length plot, okay? But we're going to still use these equations that we used in F2 to develop the plot, assuming a flange is compact. And then once we have that, all we need to do is adjust it to accommodate the limit of the non-compact flange, okay? So we'll use M sub P, right, Zx times Fy, to come up with our nominal moment capacity, but we will now be limited by the strength of the beam considering the compact flange, the non-compact flange, okay? So here's this plot. Should look familiar to you, right? Again, M sub P is Zx times Fy, okay? So if everything was good, if the section was compact, we would have that equation. And again, this is 30% residual stress, right? 1 minus 0.3 gives me 0.7. So this is my residual stress moment. This is all old news. Okay, this is elastic lateral torsional buckling in this region. Elastic lateral torsional buckling. This is plastic, if you will. Okay, assuming we're reaching our plastic moment capacity. And then here is our inelastic lateral torsional buckling. Inelastic. Okay, and I'm writing this here for a reason. Inelastic lateral torsional buckling. So now that we have a non-compact flange, we know we cannot reach M sub P. So we have to use this new equation, M sub N, which looks a lot like the equation, for this line that we saw in section F2. And once we have that nominal moment capacity, before that we know the slope, right? We know the slope of this line is going to be, again, MP minus MR, and this is going to be LR minus LP. And remember, LP is that 1.76 R sub y square root of E over Fy, right? It's this equation F2-5. That's our L sub P based on the section properties of the shape, the weak, the Ry of the section property. So we know the slope of this line, right? Slope of this line is, delta y over delta x, just like any other slope of a line. But we also can get this out of the table, right? This is out of table 3-2, okay? But once we establish the nominal moment strength using equation F3-1, now with the slope of that line, I can revise, if you will, I can revise my L sub P. Instead of my L sub P being according to F2-5, I use the slope of this line, find out where I intersect with my nominal moment that's accommodating the non-compact flange, and then that would give me my revised L sub P value. Just use a straight line equation, and once I have that, I really know that anything above that cannot be achieved. Okay, so again, this is based on C sub B of 1.0. If you have greater than C sub B of 1.0, again, it's the same concept. It just extends this out and then, magnifies this. So this would be C sub B greater than 1.0. But notice that it cannot ever get above this strength for my nominal moment, accounting for my flange local buckling. Okay. So we can take this W21/48 and use that same approach, right? So we could take this W21/48 and we can just do numerically what I just described, right? Determine the revised L sub P and then modify the plot and identify which equations apply to where, okay? So again, that's F3-1. From here down, right, this would be F2-2, and then this is F2-3, just like you've seen before, okay? And remember, so essentially, instead of in this region, right, if my unbraced length is less than my LP revised, if you will, it's based on flange local buckling. In this region, I have my inelastic lateral torsional buckling. So really, I'm just shortening up the length over which inelastic lateral torsional buckling occurs. And then over in this region, from here beyond, we have elastic lateral torsional buckling. Okay, so again, inelastic in this region, elastic here. So all we're really doing is decreasing this region, right? The region over which inelastic lateral torsional buckling occurs. Okay? So look for this example. I'll get it out there, but I want to get these lectures out to you. Okay? So hopefully that's helpful. Let me know if you have any questions.